We have the simulated uh, uh, simulation of the transmission and reception of a QAM signal, quadrature amplitude signal. So first of all, let's have a look at the message signal 1. Let's call this X1. You can see this is a single tone signal of frequency about 150 hertz. And then we have another an independent message signal X2 of another tone. Both are tone signals, so there is only one frequency. You see over here, this is about uh, about 150 hertz. Okay. Then we have another message signal X2. Okay, this is you can see the frequency is higher. It doesn't consist of any beats or any intermodulation. So this signal is again a single tone of 300 hertz. And if you see its spectrum, if you look down at its spectrum, you can see that this frequency is a little bit shifted over here. Then this peak is at 300. Okay, so it's a single tone again. So we have two independent message signals. So if you recall, what we talked earlier was now if you consider this to be the channel 1 X1 audio, X2 audio, and both are multiplied, or both are we have two product modulators, mixers, which are being used to mix X1 and X2 independently by two carriers which are in quadrature. So there's a 90-degree phase shift between sine and cosine. Okay, so we have a X1 sine over here, and then we have X2 cosine over here with a pilot carrier that which we so desire at the receiver. Why? Because to have a correct phase, we need to reconstitute the carrier at the correct phase and correct frequency so that we can bring back the spectrum to the baseband. Okay, so again we have sine omega ct, cosine omega ct over here, and then this follows that the output of the product modulator is to be followed by a low pass filter. Okay, at both channel 1 and channel 2 audio outputs. This could be an RC filter, it could have a butterworth response, a Chebyshev response, whatever you desire. Okay, with a frequency, with a cutoff frequency that is higher of any. So for example, if this is having a frequency of f1, this is having a frequency of f2, and let's say this is 150 and this is 300. Okay, then the cutoff could be about 300. So the response of both low pass filters, it could be around if you're going to use the same low pass filter. So maximum, so this is not the cutoff, this is the cutoff, so this is about 300 hertz. Okay, cutoff means that the frequency at which the response drops by 3 decibels. Okay, so if this is the magnitude response, it falls to 3 decibels. If this is the power response, it falls 50%. Then at the output, the channel 1 we derived earlier, as we have seen. This is 1/2 x1, and this is half x2. Okay, after filtering out the high frequency content, you can receive two signals x1 and x2 as they were being transmitted. Over here you have one DSB-SC signal. So there is a DSB-SC signal over here, and this is this. So we have two DSB-SC signals on the channel with carrier with your pilot carrier, which is required for the reconstitution of carrier with exact phase and frequency for demodulation. So we have two DSP-SC signals that are being transmitted on the channel, and then they are being again demodulated, bringing back bringing back the spectrum, or translating or shifting it down to the baseband. Okay, so this carrier generation is, as I've talked earlier, is almost always done with a phase lock loop. Now you will see that in the simulation, if we have, let's say, an error, a phase error of phi, it could be any phase, pi over 6, pi over 3, whatever you consider over here, there will be a deviation in the in the response of the low pass filter. You might not get x1 and x2. It will be something else. Okay, it will be something else in terms of both amplitudes and frequency. So let's have a look at those simulations. So let's say for x1 we have 150, x2 is 300. Okay, so we have x1, f1 is 150. Then we have f1 as 300. Okay, and these two tones are to be modulated by a carrier of, let's say, 1000 hertz. Okay, so we have 1000 hertz carrier signal. Okay, and we have two carriers in quadrature, so they are orthogonal. And what we have over here is a QAM signal. Okay, this is a QAM signal. So this is basically this is x1 as product of x1 multiplied by, if you recall over here, there's sine. So x1 sine plus x1 sine of omega ct plus x2 cosine of omega ct. So we have these two double sideband suppressed carrier that are being transmitted on the channel. Okay, so this is QAM signal again, and you can see that there are two peaks over here. This is one, this is second. So this is again, we have two peaks. So this, at around 1000. So let's have a look over here. We have the markers. So this is 151. Okay, this is 300. So these are the tones that are to be modulated by a carrier of 1000 hertz. And if you look here, this center frequency is of 1000 hertz. This is my carrier. Okay, this is my carrier. So at this carrier frequency, we have two double sideband signals, and you see the carrier is suppressed. We don't have a peak over here. There was no peak over here, right? So if you look at these markers, we have this about 850. So this one, 850 and 1150 is basically 150 hertz that is modulated around or shifted around 1000 hertz. That is the carrier frequency. Okay, so this shift is 150 hertz, and this corresponds to x1. Okay, and then this shifts of 300 around 1000. This corresponds to the tones of x2. Okay, so we have two DSBSC signals that can be seen over here. So these are two DSBSC signals. Okay, and the frequencies are what we are modulating. So we have 150 and 300 that we are modulating by a 1000 hertz carrier. Okay, this is what it is. Then if we are going to demodulate this with a correct phase and a frequency followed by a low pass filter, you can see that as a result we have this a time domain signal which does looks like having a frequency of about 150 hertz, as you can see over here. Okay, so it reconstructs 150 back with a correct phase and correct frequency. Again, we have 300 hertz for x2 signal when they are being multiplied by quadrature or phase shifted carriers of sine and cosine over here. So we have this we have this channel 1 and channel 2 audios that consist of the correct spectrum. So let's see what happens if we have the error. Okay, so let's say we have a phase error of pi over 3. Okay, what it means is that we have the carrier at original frequency of 1000. So this is the situation is like this. We have 2 pi 1000. Carrier is, it could be sine, it could be cosine, it doesn't matter. We have two carriers in quadrature, plus we have a phase error of pi by 3. Okay, 30 degrees offset. And what happens if you are going to multiply this cosine or sine over here in the receiver? So over here we have this plus pi over 3. Okay, we have this problem now. We have the phase error. We are not using for a PLL for, let's say, over here again. This is pi by 3. So what happens is, as you can see, we do not recover the original x1 and x2. We have some other beating phenomena. You see, you can see there is a low frequency content. Okay, there's a low frequency content like this, and then you have a high frequency content. You have a high frequency content over here as well. So we have basically two frequencies. Okay, this has become so messed up. But anyways, you can see it from here. We have the low frequency and we have another frequency. But these two frequencies are beating up together to produce a signal. This signal, which is not the signal x1. Okay, so we are not recovering x1 signal over here. We don't have it because of the phase error. So if you're not going to use a PLL, or if you're not going to reconstruct it by a correct reinserted, reconstituted carrier with the correct phase and frequency, well, then you don't have those x1 and x2 channel 1 and channel 2 audio outputs. Okay.